Hi, I'm Erin and welcome to Scopes University. Today we're going to continue on our conversation from the last InfiniiVision episode where we talked about eye diagrams. In this episode, we're going to learn a little bit more about what jitter is, what causes it, why we care about it, and how to troubleshoot it using the built-in Jitter Analysis tool on the oscilloscope. In that last InfiniiVision episode, we learned that eye diagrams can be used to help determine if there's jitter in your clock or serial data that you're working with. So let's start out by learning about what jitter actually is. If I have a serial bus or a clock signal with a specific frequency, in an ideal world, I would expect the edge crossings to occur at that exact frequency every time, directly laying over top of each other so that there are no inconsistencies in the data. But unfortunately, we don't live in an ideal world, and there are going to be times when those edge crossings come in a little too early or a little too late. So jitter is the deviation of where that edge crossing actually ends up compared to where it ideally should be. And this is oftentimes called time interval error, or TIE. And typically there's a specification called a jitter budget as to the allotted amount of jitter in a signal. So if we think back to the eye diagram from that last episode, there was a lot of jitter on the signal we were working with. So we're going to figure out how to fix that in our design. But first, let's talk about some of the causes of jitter. Jitter can be caused by a lot of different things. There's system phenomena, there's data-dependent phenomena, and random noise. System phenomena is caused by things that are actually happening on your board. So it consists of things like crosstalk or impedance mismatching. Data-dependent phenomena can be things like intersymbol interference, or ISI, and duty cycle distortion. So these things can be caused by inconsistency in writing data. And random noise can be thermal noise, which is related to temperature. So the higher the temperature, the more noise there is. Shot noise, which is related to electrons and hole phenomena, and pink noise, which is related to frequency. So the lower the frequency, the higher the noise. And these are all just an unfortunate fact of life, and they're all going to have some sort of Gaussian distribution effect on your signal, and there's really nothing that we can do about these. So now we know what jitter is and what causes it, but why do we even care about it? I talked a little bit about this in the last episode, but if you have too much jitter in your signal, it's ultimately going to cause errors in the data that you're transmitting. So the receiving end is going to be interpreting the bits incorrectly because the edge crossings aren't happening when they should be. So now let's do some analysis on that signal we were working with on the oscilloscope using that built-in Jitter Analysis tool. So we're going to figure out specifically what it is that's causing the jitter in this signal that we're working with and how we can go about fixing it in our design. How the histogram is set up, it shows us the distribution of edge crossings, and the height of the histogram is correlated to the odds that an actual edge will be that far away from the ideal edge. Also, notice the automatic measurements that were brought up when the histogram was created. We can actually learn a lot just from the shape of the histogram. So if we're seeing more of a bimodal shape, this is indicative of deterministic jitter, which is caused by system or data-dependent phenomena. If we're seeing more of a Gaussian distribution effect, this means we're working with random jitter, which is caused by random noise. And again, this is just an unfortunate fact of life that we really can't do too much about. From the histogram we can see on screen here, we see there's a strong Gaussian component, which again is caused by random jitter, and there's also a strong bimodal component, which again is caused by deterministic jitter. And we can also see there are some outliers down in the lower right side of the histogram as well. So let's view this timing error in another display format that may reveal some additional information about this jitter that we're seeing. So we already learned what we can from the histogram, so the first thing I want to do is turn off my real-time eye and bring that signal back up on screen. And I want to zoom out a little bit on my signal here, and then we'll go into the jitter menu. And the first thing we want to do in here is select a jitter measurement. So the first thing I want to look at is the data time interval error. So I'll select that, and I'll just leave it at the default settings. We're looking at channel 1 and that measurement I wanted to look at, so I'll just press OK. And ultimately what I want to look at here is a measurement trend of that time interval error data that I'm collecting. So I'm going to auto set up a measurement trend, and now I can see my measurement trend on screen here in purple. So the trend waveform that we're seeing now is a plot of the timing errors of each of the data edges relative to the recovered clock, the vertical axis, versus time, the horizontal axis. And this waveform is time correlated to the captured serial data signal, the yellow trace. From the trend plot, we can see that our data signal has sinusoidal modulation, which correlates to the bimodal distribution of the jitter histogram plot that we saw. In addition to the sinusoidal modulation, it appears that our data signal has the occasional extreme positive timing error, as evidenced by the spikes that we're seeing in the trend waveform. And this is what is producing those outliers that we saw in the histogram. Determining the frequency of the modulation might provide a clue as to the source of the jitter. We can turn on the Jitter Spectrum view to figure this out. So to do that, I'm going to go back into the Jitter menu, and then I'm going to select Auto Setup Jitter Spectrum. Now if I close out of this, I'll see an FFT showing the spectrum analysis of this jitter. So the spectrum view is provided by running an FFT math operation on that trend waveform. So this allows us to find the frequency of the modulation. And let me just move my signals around a little bit so we're able to see this a little bit better. So we can see there's a peak in the FFT, and that's being caused by the sinusoidal modulation on our signal. So to take a look at what the frequency is of that peak, all we have to do is go into the search menu, select the search soft key and change it to frequency peaks, and change our source to math 4. Now we can see that that frequency peak is about 19 kilohertz. To eliminate this 19 kilohertz sinusoidal modulation, we can simulate a first order phase lock loop, or PLL, clock recovery algorithm on the oscilloscope. A PLL helps to reduce the amount of jitter you're seeing because it keeps the input and output phases locked, which keeps the input and output frequencies the same, therefore filtering out any unwanted frequencies in that range. So to implement that phase lock loop and see the effects, I'm going to default setup and auto scale. And I want to set up my real-time eye again, so we'll go into the Analyze menu and select Features and select Real-Time Eye. Then I'll go into the Clock Recovery menu, and we're going to change the method to first order PLL. So this will simulate the PLL on the signal. Now if you can remember from the last video, our nominal data rate for this signal was 6.2 megabits per second. And we're going to specify a loop bandwidth of 200 kilohertz. That should filter out that 19 kilohertz sinusoidal modulation that we saw. So you have to be careful when you're selecting the bandwidth that you want to use for this loop filter. A bandwidth too low might not filter out enough jitter, and a bandwidth too high might end up filtering out some of your signal, which isn't good either. So you can play around with different bandwidths a little bit to get an idea of what's going to work for your signal. Now I can select OK and auto set up my eye diagram. Now I can already see that the jitter on this eye diagram has improved greatly. We got rid of a lot of the jitter that was riding on this signal, and we're seeing a much cleaner eye now. And if I bring the histogram back up, we see the shape is beginning to look much less bimodal and much more Gaussian. We've eliminated all of the deterministic jitter, and all we're left with is the random jitter, which again, we really aren't able to do much about. If you're seeing very bad random jitter that will cause errors in the data you transmit, kind of like we're seeing on the signal here, you might have to actually go back and redesign that component. And if you want to learn a little bit more about some of the other jitter measurements available, be sure to check out the 2-Minute Guru episode on basic jitter measurements. Daniel talks a little bit more in depth about a few of the other measurements. So now you know what jitter is and why you should care about it, as well as how to troubleshoot it if you do see it in your system. With the steps that we covered today, you'll be able to identify what it is that's causing the jitter in your system and what your options are to fix it. If you want to learn even more about jitter analysis, make sure you check out the Jitter Analysis application note. And if there are any specific topics you'd like to learn about in future episodes, make sure you leave that in the comments below. Make sure you subscribe to our YouTube channel to see more videos like this, and like us on Facebook, Instagram, and Twitter.